Good morning, students. Welcome to the lecture of real analysis. In the last lecture, we have seen some important theorems regarding the integrability of the function. In the first theorem, we have proved that if the function f is bounded and integrable on each of the intervals ab, ac, and cb, then we have proved that integration a to b is equal to integration a to c plus integration c to b. To prove this equality statement, we are going to use the mathematical analysis part. To prove this statement, we want to prove that modulus of difference of left side and right side is less than by epsilon, and to do so we have just made use of the Riemann sum definition. To use the Riemann sum definition, we have used Riemann sum definition, and also we have stated that sum of Riemann sum on the closed interval AB is equal to Riemann sum on AC plus Riemann sum on CB, and with the help of this and with few mathematical steps, we have proved that the difference and modulus of left hand side and right hand side is less than by epsilon, which actually proves us that the two terms are equal. The second theorem we have proved is every continuous function is integrable. Actually, these theorems is going to help us to give the aspects for checking whether the function is going to be integrable or not. In order to prove the continuous function is integrable, we have made use of the fact that continuous function depend on the closed interval is uniformly continuous. I forgot to write one more point here. Continuous function on closed interval is bounded also, because here we have to mention boundedness, no? And bounded on closed interval AB. Therefore, as it is bounded and uniformly continuous, by the definition of uniform continuity, we have written there exists a small positive number eta greater than 0. For eta greater than 0, there exists delta greater than 0, such that according to the definition, this is mod of ft1 minus ft2 less than eta, and for mod t1 minus t2 less than delta. We have denoted this by equation number 1, and knowing that partition P is selected in such a way that the norm is less than delta. If the norm is less than delta, therefore for any 2 points in that corresponding partition or the subinterval, one can use this equation number 1. And using this, we have written for I plus subinterval, capital Mi minus Mi, small mi is less than eta. And with this, we have proved that UPF minus LPF is less than epsilon, proving the function is integrable under closed interval. Second theorem we have proved is the function which is monotonic on closed interval AB is integrable. Whenever we are using the word monotonic, there are two types of function. One is monotonically increasing, second is monotonically decreasing. And in the last lecture, we have seen what is the difference between monotonically increasing and strictly increasing. Though as the nature of the function is monotonic, the function is going to be bounded surely on the closed interval AB. We have started the proof by considering the function to be monotonically increasing. Then by knowing this function is monotonically increasing, we have just noted the values of capital Mi and small mi, and those values are respectively f of x and f of xi minus 1. And this we have written for the partitions P with norm less than eta. Again, with few mathematical steps, we have proved that this UPF minus LPF is less than epsilon. Right? Here, particularly, we have to choose the value of eta. Eta times FB minus FA less than epsilon actually, but if we shift that FB minus FA on the right, this denominator may become 0. Therefore, just to reduce that case, or just to avoid that case, we have written plus 1 here. And finally, we have proved that UPF minus LPF is less than epsilon, proving the function is integrable. Monotonically increasing function is integrable. Similarly, one can prove the result for monotonically decreasing function, and combining both, one can say that the function which is monotonic is integrable. Now let us come in today's lecture. In today's lecture, we are going to study new facts about the integrability, important theorems. The first theorem we are going to study today is we want to prove that a bounded function having finite number of points of discontinuities is also integrable. Actually, in the last theorem, last lecture, we have proved a theorem. Every continuous is integrable. Therefore, it doesn't mean that discontinuous function is not integrable. Right now, therefore, in today's lecture, we are proving a theorem: a function having finite number of points of discontinuities is also integrable. Let me write the statement. The theorem statement is a bounded function f having a finite number of points of discontinuity, finite number of points of discontinuity on closed interval AB, then prove that f is integrable. F is integrable on closed interval AB. On closed interval AB. Before going to the textbook proof of this theorem, I will write the textbook proof in blue link afterwards. Before that, we will just try to understand how the theme of the proof is being developed. Okay. Here, what is the assumption? Function is bounded. Also, it has finite number of discontinuities. Therefore, time being, we will assume the function has p points of discontinuity. P points of discontinuities, right? If I'm going to assume there are p points of discontinuities, the partition of the function, partition of the interval we will do in such a way that every point of discontinuity is covered in one of the subintervals. Okay, let me show you how we are going to make this. Suppose this is the closed interval a to b under the consideration, and let me just plot the points of discontinuities. P points of discontinuities like this. Say these are some p points of discontinuities. Now we are going to mark the partition of this closed interval AB such that these p points of discontinuities gets covered in every subinterval. Therefore, what we will do, as this is the first point of discontinuity, I will mark the point around this first point of discontinuity. Therefore, these are the 2 points in the partition we are going to select. Therefore, the first point of discontinuity is covered in one of the subintervals. Similarly, for the second point of discontinuity, we will make the we will plot the 2 points around it so that it is covered in the interval. Similarly, this third point is being covered in one of the subinterval, and lastly this fifth point also will get covered under the subinterval. Therefore, how many points I have to plot in the partition so that these p points of discontinuities will get covered in one of the subintervals? Are you getting my question? There are p points of discontinuities. To cover the first point of discontinuities, we have plotted 2 points around it. No? 1 point to the left of discontinuity, 1 point to the right of discontinuity, so that this first point of discontinuity get covered in the interval. For the second, we have plotted 2 points. For the third, we have plotted 2 points. Therefore, how many points of discontinuities are there actually? P points of discontinuities are there. Therefore, how many points I have to plot in the partition? To cover p points of discontinuity, may I say I have to plot 2p points? Yes, 2p points to be plotted. Correct, na? 2p points to be plotted. Okay. And how many subintervals we have formed then? How many subintervals of this partition A to B is being formed? See, like this now. If this is my closed interval A to B, and if I plot only 1 point, then how many subintervals are there? How many subintervals? By plotting one point in the interval.
P.
2.
2 points. Correct. If I plot 2 points, how many subintervals?
3.
3. If I plot 3 points, yes, 4
4.
subintervals. No? Yes or no? Is the voice clearly audible
Yes,
to
ma'am.
everyone?
Yes.
Yes, ma'am.
पण
Yes,
मध्ये
ma'am.
मध्ये ब्रेक व्हायलाय मॅम.
Acha, very good. Let me just increase the voice. Now, students, check. Is the voice clear now?
Yes, ma'am.
Yes, ma'am.
Good.
Yes, ma'am.
But now, yes. Now, if we plot only one point in the closed interval, it gives me two subintervals. If we plot 2 points, it gives us three subintervals. If we plot 3 points, it gives us four subintervals. Now, here, how many points we have plotted?
3 points.
Two. No, two p points we have plotted to cover p points of discontinuity. Therefore, how many subintervals are formed? Is it so difficult? 2p plus 1, na? Correct or not?
Yes, ma'am.
2p
Yes,
plus
ma'am.
2p plus 1 सबइंटरवल. जेवढे पॉइंट्स प्लॉट करतो त्यापेक्षा एक जास्त इंटरवल तयार होतो ना. For 1 point, 2 intervals. For 2 points, 3 intervals. For 3 points, 4 intervals. Therefore, for 2p points, 2p plus 1 subintervals. Okay? Is it clear up to this? What process we are going to follow? We have assumed
Yes,
we
ma'am.
have assumed there are p points of discontinuity and we want to prove the function is integrable. Therefore, to prove the integrability of this, to cover these p points of discontinuities, what we have done, we have plotted the points of the partition in such a way that every discontinuity gets covered in one subinterval. For one discontinuity, there is one subinterval. Therefore, to cover p points of discontinuities, we have plotted in all 2p points in the closed interval, and due to this 2p points plotted, we have obtained 2p plus 1 subintervals. We have obtained 2p plus 1 subintervals. Okay. Is it clear to everyone? Now, out of those 2p plus 1 subintervals, time being, in order to understand the theorem in a neat manner, what we will do, we will divide the intervals as p intervals and p plus 1 intervals, and whichever the p subintervals are there, covering p points of discontinuity, time being assume that these are the first p intervals. These are the first p intervals. Okay, so this is x1, x2 to xp. How many points, how many subintervals are there? This is first, second, and continue up to pth subinterval. Continue xp plus 1, xp plus 2, and last this is up to xnc. Okay, time being, see what I'm saying, time being, in order to understand the theorem, what I'm going to assume, let us assume the p subintervals covering the points of discontinuity are adjusted in first p subinterval. How many subintervals are remaining with us then? How many subintervals are remaining? P plus 1? Correct,
Yes,
na?
ma'am.
Okay. Now what we are going to do, if I'm collecting the points of discontinuity in first p subintervals, may I say the function is continuous over this remaining p plus 1 subintervals. Over these remaining p plus 1 subintervals. In order to show the function is integrable, no doubt what is the aim to show condition of integrability. That is UPF minus LPF is less than epsilon. Therefore, let me write what is UPF minus LPF. This is not the way of proof we are writing in the exam. This is just for the sake of your understanding. This is summation I equals to 1 to n. May I write directly capital Mi minus small mi into delta xi. Now we will divide the sum into two parts. First p subintervals and remaining p plus 1 subinterval. This is summation I equal to 1 to p capital Mi into minus small mi into delta xi added with summation I equals to p plus 1 to n capital Mi minus small mi into delta xi. Now, what is the job to prove the sum of these summation of these two sum of these two summations is less than by epsilon. Therefore, what we are trying to adjust is sum due to the value due to the first sum is less than epsilon by 2. Also, the value due to the second sum is less than by epsilon by 2. Now, what about capital Mi minus small mi? Capital Mi minus small mi are the oscillations of the function in ith subinterval, correct? Oscillations of f in ith subinterval. What about m minus m? What about m minus 1? These are also oscillations of f in whole interval, no? Closed a to b. Then can anyone tell me the relation between these two inequalities and these two numbers? Relation between these two numbers. Three options you have: equal to, less equal, and greater equal.
Less equal.
Yes, it is less equal. Why it is? Because ith subinterval is the subset of your closed interval. That's why oscillations of the function in ith subinterval must be less equal by capital M minus M. Whether anyone is having a doubt on this?
No, ma'am.
Good. Therefore, let me substitute the value here in the above statement. Therefore, what it will be? UPF minus ELPF. May I say it is less equal now? This is less equal. Summation capital M minus M into delta xi, I running from 1 to p. Second summation as it is, I equals to p plus 1 to n capital Mi minus small mi into delta xi into delta xi. Now look at the first summation. Consider the first one. As this term m minus m is independent of I, may I take it outside the sum? This is m minus m summation I equals to 1 to n into delta xi. Now, what is delta xi? Summation delta xi is length of these first p subintervals. Correct now? Sum of length of these first p subintervals. Now, if I want to show that the contribution by this first sum is less than epsilon by 2, also the contribution by this is also less than by 2. This is the aim. Okay, this is the aim to show. Therefore, in order to show this term is less than by epsilon by 2, may I say one can adjust the length of first p subintervals containing p points of discontinuity to be less than. What I want to adjust? I want to adjust this term less than by epsilon by 2. Therefore, may I say sum delta xi can be adjusted less than epsilon upon 2 times m minus m. Is it okay to everyone?
Yes, ma'am.
We want to plot the p intervals in such a way that sum of length of these first subintervals containing p points of discontinuity is less than epsilon upon 2 times m minus 1. Why we have selected this quantity? Because if I put this value here, the contribution to UPF minus LPF will be less than epsilon by 2. Correct now? Therefore, what this above equation becomes? Summation I equals to 1 to p capital M minus M into delta xi becomes strictly less capital M minus M as it is. We have adjusted this summation delta xi to be less than epsilon upon 2 times M minus M. Okay, then what is the value? This is epsilon by 2. Therefore, contribution by the first summation we have proved less than by epsilon by 2. Now, Similarly, we have to go for the contribution of the second term to the difference UPF minus LPF is less than by epsilon by 2. But the fact is known to us that over these remaining p plus 1 subintervals, the function is continuous. The function is continuous, and in the last lecture itself we have proved that if the function is continuous, then it is integrable. Therefore, one can say that over these p plus 1 intervals, the function must be integrable. And if the function is integrable, one can adjust the value of the difference UPF and UPF minus LPF is less than by epsilon. Let me do that. Now what we are going to do? We are going to find out the contribution to the difference on this interval. What is the length of this interval? Xp plus 1 minus Xp. Now we want to adjust the total contribution on these interval to be less than epsilon by 2. Therefore, what should be a contribution to the difference UPF minus LPF on this one interval? On one interval, if I write contribution to the difference UPF minus LPF by second sum on one subinterval. On one subinterval, this should be less than epsilon, but we want to adjust the terms. Therefore, I will write this as less than epsilon upon 2 times p plus 1. Epsilon upon 2 times p plus 1. Why I have written p plus 1? Contribution to the difference is epsilon upon 2 times p plus 1 by one interval. Then what is the contribution by p plus 1 interval? This is also epsilon upon 2 times p plus 1. For the last also the contribution to the difference is epsilon times 2 upon p plus 1. So this is p plus 1 times, na? P plus 1 times epsilon upon 2 times p plus 1. Therefore, it will get cancelled. So just a part of adjustment. Therefore, on one subinterval we have adjusted this. Therefore, contribution to the difference UPF minus LPF by second sum on p plus 1 subintervals. On one subinterval we have made it as less than epsilon upon 2 times p plus 1. Then on p plus 1 subintervals, how much is the contribution? This is p plus 1 times epsilon upon 2 times p plus 1, which is actually epsilon upon 2. Therefore, here we have made this contribution is also epsilon by 2. Therefore, together how much it is giving us the value? I will call this to be statement number 1.
Epsilon.
Yes, it is epsilon. Now I will call this as 1. Therefore, equation 1 becomes UPF minus ELPF less than first term, first summation we have made it less than by epsilon, na? Less than by epsilon by 2. For the second also we have made it as less than epsilon by 2. One can write directly also. Why? Because on this remaining p plus 1 subinterval the function is continuous. On the remaining subintervals function is continuous, every continuous, integrable. Therefore, by condition of integrability, one can write directly less than by epsilon by 2. But why we have written like this? Because coming to this position again, it is not guaranteed that those p plus 1 subintervals were coming together. Therefore, we have made this is the first subinterval. This is the second subinterval. This is the third subinterval on which the function is continuous. Those subintervals are not necessarily always coming together. Okay. Therefore, we have to write the contribution by each subinterval. Okay. We have to write the contribution by each subinterval on which the function is continuous, and finally we have to add the contribution, right? Therefore, understood the fact, we have made this UPF minus LPF less than epsilon finally. What steps we have followed? Just let me recall. We have started with an assumption there are P points of discontinuity. All those P points we have plotted initially by green dots. Okay. Then later, to cover these P points of discontinuities, we have plotted 2 points to every point of discontinuity around it in order to cover the discontinuity in one subinterval. One point of discontinuity will be covered in one subinterval, right? Therefore, to cover P points of discontinuity, we have to plot 2P points. We have to plot 2P points on the closed interval AB. Due to these 2P points, there are 2P plus 1 subintervals. There are 2P plus 1 subintervals. For the sake of understanding the theme, what we have done, we have plotted the P points covering the points of discontinuity as first P points, and the remaining P points, P plus 1 subintervals, we have taken afterwards. Therefore, on the remaining subintervals, on the remaining P plus 1 subintervals, no doubt the function is going to be continuous. Correct now? On these P plus 1 subpoint, the function is going to be continuous. Therefore, it is integrable. Therefore, the UPF minus LPF value can be made less than epsilon. Question is about the first P subintervals in which every subinterval is containing one point of discontinuity. Therefore, to find out the contribution, we have just divided the summation into two parts. First part containing P points of discontinuity, and the second part function is going to be continuous. Later, we have understood the relation between mi, capital Mi, small mi, oscillations of the function in the ith subinterval, and oscillations of the function on whole subinterval AB. And the obvious relation will be capital Mi minus small mi is less equal by m minus m. If putting the value here, we got the first sum as summation I equals to 1 to p m minus 1 m into delta xi. Taking m minus m out, we get summation delta xi. In order to adjust the term less than by epsilon by 2, what adjustment we have made? Summation delta xi are found in such a way that, or the points are plotted in such a way that the sum of the length of subintervals is less than epsilon upon 2 times m minus m. Clearly, if I put the value here, the total value must be less than epsilon by 2. That is, contribution by the first summation we have made less than epsilon by 2. Over the remaining P plus 1 subintervals, no doubt the function is continuous, hence integrable. Therefore, the contribution to UPF minus LPF can be made less than epsilon by 2. To make this as less than epsilon by 2, we have found the contribution by one subinterval on which the function is continuous. Okay, on these subintervals. Why we are writing on one subinterval? Because as per this diagram, the subintervals over which the function is continuous is not necessarily are coming together. These are splitted like this. Okay, therefore this is the interval over which the function is continuous. Second interval is here, third interval is here, fourth interval, and so on. Therefore, we have found the contribution to the difference UPF minus LPF by first interval, by one interval, and we can adjust, as the function is integrable on that subinterval, we can adjust UPF minus LPF to be less than epsilon upon 2 times P plus 1. This is by one subinterval. In all, we have P plus 1 subinterval. Therefore, the contribution to the difference by P plus 1 subintervals must be P plus 1 times epsilon upon 2 times P plus 1. Together, we can make this as epsilon by 2. Therefore, the contribution by first summation we have made less than epsilon by 2. Contribution to the by the second summation we have made less than by epsilon by 2. Finally, this is less than epsilon, and hence the function is integrable. Hence the function is integrable, having finite number of points of discontinuity. But this is not the way you are going to write it in the exam. I will write the textbook proof now. Is the idea clearly understood?
Yes, ma'am.
Okay. Now what we will do, we will write the textbook proof of this theorem. Let me start the proof. If the concept was understood, whatever I am writing as a textbook proof, there should not be a difficulty. Let the set of points, let the set of points of discontinuity of F have finite number of finite number p finite number of points of this. Let the set of, okay, sorry, let me change the statement. Let the bounded function, let the bounded function f has finite points of discontinuity on closed interval a to b. Let p number of points of discontinuity. How many number of points of discontinuity we have assumed? P number of points of discontinuity on closed interval AB. Okay. Similarly, we will start with epsilon greater than 0, be given number. Be given number. Now I will write the partition, how to select. We now consider a partition P of closed interval AB such that for all the points of discontinuity, gets enclosed in P non-overlapping subintervals, comma, the sum of whose lengths is less than. Now see, here I am writing epsilon upon 2 times m minus m, which we have already written here. Na? Summation delta xi should be chosen like this. And here we have seen why the need is to select like this. Now, whatever is this number small, however the number epsilon upon 2 times p plus 2 times m minus m is small, we can make the interval so small such that the statement is going to be true. लक्षात येते का? epsilon upon 2 times m minus 1, m minus m हा जरी किती छोटा नंबर असेल तरी हे सिलेक्शन आपल्या हातात आहे ना सब इंटरवलचं. हे इतके जवळजवळ सिलेक्ट करायचे पॉइंट्स. ओके, इथे अगदी जवळ त्याच्या, जेणेकरून तो समेशन डेल्टा एक्स आहे लेस दॅन epsilon upon 2 times m minus 1 कव्हर झाला पाहिजे, m minus m कव्हर झाला पाहिजे. ओके, therefore this is the selection we have made. Next, we will make the selection for oscillations. The oscillations of F in ith subinterval is capital Mi minus Mi, and oscillations of F on closed interval AB is capital M minus M, which implies capital Mi minus small mi is less than or equals to capital M minus M. That is, the oscillation of F in each of these subintervals, being less than or equals to capital M minus M. Capital M minus M. Now we will write the total contribution by these P subintervals enclosing P points of discontinuity. Now we will write their total contribution to the difference UPF minus LPF is less than that. What is the total contribution now? We have seen capital M minus M into epsilon upon 2 times M minus M, which is equal to epsilon by 2. Here we have written contribution by these P subintervals containing P points of discontinuity is less than M minus M into summation delta x. So summation delta x we have selected this. So the total contribution is less than epsilon by 2. Total contribution is less than by epsilon by 2. Let me call this as statement number 1. Now what about the remaining subintervals? On the remaining subintervals, the function is surely continuous. Therefore, the contribution we will check. The function f is continuous in the remaining portion of closed interval AB. That is in the P plus 1 subintervals of closed interval AB, excluding P subintervals considered above. Okay. Now what about this remaining P plus subinterval? We will find out the contribution by one subinterval and then finally we will write the contribution by in all P plus 1 subintervals. Now we will write as we know that every continuous function is integrable. Every continuous function is integrable. Therefore, the contribution to the difference UPF minus LPF from each of the subinterval. Each of the subinterval can be made less than epsilon upon 2 times P plus 1. Understood now why I am taking this P plus 1 in the denominator? Because this is the contribution by one subinterval. Okay. And therefore, how many subintervals we have? Not P plus 1. The contribution totally will be P plus 1 into epsilon upon 2 times P plus 1. So that P plus 1 will get cancelled and we will get only epsilon by 2. Is it clear to everyone?
Yes, ma'am.
Now I will write so that the total contribution to UPF minus LPF by these P plus 1 subintervals. P plus 1 subintervals is less than P plus 1 times epsilon upon 2 times P plus 1, which is equal to epsilon by 2. Let me call it as statement number 2. This is statement number 2. Now we will write the total contribution by P subintervals and P plus 1 subintervals. Thus, for the partition P of closed interval AB, the total contribution to the difference by the subintervals which contains P points of discontinuity, and by remaining subintervals is what is the total contribution is less than by epsilon by 2 plus epsilon by 2. Here I can write UPF minus LPF is less than epsilon by 2. Epsilon by 2 reason this is from 1 and 2. Correct? Therefore, finally we have proved UPF minus LPF is less than by epsilon. Hence the bounded function F having finite points of discontinuity is integrable. Finite points of discontinuity is integrable. Hence the proof of this theorem. If you have any doubts, you can ask me. If the proof to this theorem is understood, then remaining proof to the second theorem is also on the parallel lines. Any doubt on this proof?
No, ma'am.
Good. Now I'll take one more theorem stating that the function having finite limit points to the set of points of discontinuity is also integrable. Let me write a bounded function F is integrable on closed interval AB. I write initially prove that. Prove that a bounded function F is integrable on closed interval AB if the set of points of discontinuity has only finite number of limit points. Can anyone tell me how many number of points of discontinuity it will have then? Statement says that for the set of points of discontinuity has finite number of limit points. Therefore, actually how many points of discontinuity are there? In this theorem, we have taken finite points of discontinuity. Now we have moved towards the second theorem, which states that set of points of discontinuity has finite number of limits. Therefore, can anyone tell me how many number of points of discontinuity will be there? Whether it is finite? Yes or no? Whether the points of discontinuity are finite in number?
Yes, ma'am.
Finite in number? means the set of points of discontinuity has finite points only. If it has finite points, can you find the limit point? Can we find the limit point for a finite set is the question. Students, it is given that it has limit points. For how many points are there in that set? If it has finite number of points, whether limit point exists. Whether limit point exists for the finite set, yes or no?
No.
No, it is not. Correct. For how many points we should have? Infinite points we should have in the set of discontinuities. Set of points of discontinuity. Clear now? Therefore, first theorem we have seen initially continuous is integrable. Second, we have seen finite points of discontinuity. If it has, then also integrable. Now we have came to the third one, which says that it has infinite points of discontinuity, but if it has finite limit points, then the function is integrable. Now, very similar to the previous theorem, what we are going to do? We are going to find out the contribution by the intervals for the finite limit points and for the remaining ones. Okay, let us plot this partition. Again, we have finite number of limit points or set of points of discontinuity. Let me assume there are p limit points. There are p limit points or set of points of discontinuity. Surely this set is having infinite points, infinite discontinuity points, right? Therefore, if I take the p limit points like this, these are my p limit points, say. Okay, these are my p limit points, say. Again, we will find out. Same process we are going to cover. We will cover the limit points in the subintervals. If I take p limit points, there are 2p plus 2p points and 2p plus 1 subintervals. Okay. Now what is our job? Our job is to make the contribution by these subintervals less than epsilon by 2, and for the remaining subintervals also it is less than by epsilon by 2. Very similar to the previous one. You have to answer me one question. If I am going to cover the limit point in the subintervals like this, how many points of discontinuities are there outside these subintervals? How many limit points are there outside these subintervals? Suppose this is the first limit point. This is first limit point. This is second limit point. Continue. This is my pth limit point. And we have plotted the suitable intervals around every limit point. The question is, how many points of discontinuity are there still in the outside intervals or in these remaining subintervals? There are two possibilities. You have infinite discontinuity points or you have finite discontinuity points. Can anyone tell me the definition of a limit point? Limit point of a set. Two different definitions I have told you actually of the limit point of the set. Correct, na? Can anyone repeat the definition of limit point? I hope I am clearly audible to all the students. So this is the reason why we have taken the basic concepts at the starting of our lectures.
If zeta is a limit point of a
Hmm?
set S, then every neighborhood of zeta contain infinite number of points of S.
Good. Now
And
what
second
is
definition is
uh,
at least one point other than zeta.
okay, here we will use first definition only. Okay. Therefore, what is my set? Yes, under the consideration points of discontinuity. Correct, na? Correct, na? What is the set? Under the consideration set of points of discontinuity. Now, if this is the set of points of discontinuity, if zeta is the limit point, every neighborhood of zeta is going to contain, this is said, yes, every neighborhood of zeta is going to contain infinite points of the given set. Okay, this set yes has infinite points, no doubt. Okay, now here how many limit points we have? P limit points. Therefore, every limit point is going to contain infinite points of discontinuity.
Yes, ma'am.
Infinite points of discontinuity. Correct. Means first subinterval contains infinite points of discontinuity. Second interval contains infinite number of discontinuity. Third also contain infinite discontinuity. Last also contains infinite. Then how many points of discontinuity remains outside these intervals? Probably there is no point of discontinuity. Probably there is no point or finite parts. Correct, na? We cannot say it is no because we don't have a guarantee that there is no point of discontinuity outside these. Therefore, one can say that as those infinite points of discontinuities are getting covered in these sub-interval, but still there may be finite discontinuity points are outside these subintervals. Is everyone clear with me? Finite points of discontinuity may be there outside these subintervals. Therefore, whatever the remaining subintervals, I will mark the subintervals. This is the remaining, this is the remaining, this is the remaining. Correct? This is also a remaining. Therefore, these remaining subintervals contains finite discontinuity points, na? Yes or no? These
Yes,
remaining
ma'am.
subintervals contains finite discontinuity points. And by the previous theorem we have seen if the function contains finite points of discontinuity, then also the function is integrable. Then also the function is integrable. Means here is the situation. But as similarly to previous example. First, p points of discontinuity are covered in the p subintervals. Over remaining subintervals, function is continuous and hence integrable. Okay. Likewise, these p limit points of set of points of discontinuity covers maximum number of points of discontinuities, and over the remaining subintervals there may be finite discontinuity points, and over the remaining subinterval function is surely integrable by the previous theorem. By the previous theorem. Therefore, what is the job in this section? What is the job in this section we are going to do? Again, we will make the sum of length of p subintervals. Again, here I am writing UPF minus LPF is equal to summation capital Mi minus small mi into delta xi. Now I am going to divide this into two parts. First capital Mi minus Mi into delta xi. Now this is these are the subintervals we have selected. P subintervals containing limit points. Containing limit point. What about the remaining sum? This is over the subintervals, remaining subintervals, covering finite number of discontinuities. Now what we want to make, the total contribution is less than epsilon by 2. Therefore the job is to adjust this term less than epsilon by 2 added with this term less than epsilon by 2. Correct? Therefore here for the first one, what we are going to do, we will make the sum of p subintervals, a sum of length of p subintervals less than epsilon upon 2 times m minus m as selected in the previous theorem. And what about the oscillation? Oscillation in above p subintervals, oscillations of f in above p subintervals can be made less than m minus m, right? Then what about this equation? This is what we want to do. Therefore this above equation number 1 can be written as, what about the first one, first summation giving me, this is less than epsilon upon 2 times m minus m into m minus 1. And what from the second one we are going to adjust epsilon by 2. To put together this is epsilon by 2, which is epsilon. Is it clear to everybody? Proof goes very parallel to the first or the previous theorem or today's lecture. Okay? But this is not the textbook proof. What I will do, I will take the textbook proof in the next lecture because it is almost 1. We have to stop the lecture for today. If you have a doubt in this section, you can ask me. Textbook proof carries 5 minutes only, that we will cover in the next lecture. Okay, thank you for watching the lecture.